In this task I'll navigate DSP Speedster, show you around it a bit, and have a look at some of the features. First, go to the MATLAB command line, type Speedster. Up comes a parameter which is the underlying fixed sampling frequency of 20 kilohertz. That can be changed. You could type sim setup of some other number like 40 kilohertz, and that would reset everything. I'm going to go back to 20,000 hertz because that's quite handy for a lot of audio demonstrations and so forth. Here's what comes up. This is the splash panel of DSP Speedster, and it's an array of little directories here, little libraries, which have got things like the green ones here. These two are to do with signal sources. If I look inside them, I'll see things like sine waves, noise generators, so forth. And I can get more complicated ones by going to the next one, which is got chirps and various sorts of pulses and so forth. There's quite a large number of these blocks, and it takes a while to find out where they all are. So a lot of people prefer to start in the express lane directory, which is down here. And here we've lifted out from each of the directories just some particularly frequently used blocks. You can then, of course, return to that main library, for example, where the signal generators were, by clicking inside there. So quite often people should start, I think, in the early days of their use with Speedster, with this particular little directory here. There's various ways to display signals, quite a number of them. We have multi-trace scopes, we have spectrograms, we have filter analyzers, lots of things. We'll see a few of these in action in just a moment. There are help files for the various analyzers. These are quite sophisticated devices, and it's simply a matter of clicking on here and getting help for that particular directory, that particular device. It shows how it's used and what you can do with it. In more general terms, if I go out of this directory, we can get a general help for DSP Speedster by clicking there. And this also gives you the links to these various other analyzers that I talked about for the analyzer helps, or the more general one, which is showing you the layout and what the cluster of different blocks do and so forth. I'll just take you through some of that right now. You've got also an infrastructure block for wiring up models. You need quite a lot of little things like adders, multipliers, and so forth. And this is an extreme library in the sense that there's quite a number in here in the shaded section. Now these are the sections where we've lifted directly and made local residence for blocks which come straight from Simulink and or Simulink's DSP block set. Well, signal processing block set they call it nowadays. The blocks that are to do with Speedster are shown in the other areas, and they tend to be thematically grouped. So the infrastructure, in this particular case, we're showing a lot of them that we like and that we need to use from main Simulink. And other blocks, for example, might not be so heavily populated. If we look at our general filters, we have quite a big filtering theme. Here are a few of the blocks that we've taken and made resident here in Speedster. And so these are what we call native to Simulink and signal processing block set. So these are our blocks. Quite often they're constructed by these elemental blocks, which are to be found in the signal processing block set. You can always look inside of a block by putting it here. You hit a white piece of paper. This gives you a model. That model is imbued with that default sample frequency I mentioned a while ago. And if we lift just this one in here, all we have to do is a left click and drag. There are help connections here as to how to do the drawing operation with Simulink features that really is best done by looking at the Simulink help. Right click allows you to look under a mask if there is a mask that's being used. So here, that's what's happening here, and here's one of the blocks one level down. So you can see multi-layers and some of the blocks going quite far down. So I don't know if I take another one. Here's some other filter. Look inside that. That's a similar situation, but of course they have different controlling software. Let me get another one. I know this one will be a bit more sophisticated. I look inside there, and there's a filter, and there's also something else happening, some constant. So you can, to a certain extent, in fact for most of our blocks, see what's inside. This is very important because this allows you to decide if you agree or disagree with the how the algorithm has been done. But of course each block in most cases, blocks have help files which you can access right here. There's one, for example. So this tells something about the help file as to how it's been done and so forth. So if I get rid of those elements, I might just keep this blank model for constructing something else in a moment. We have lots of these filters, and very rarely do you go very deep down to have to struggle and find things. Here's a case where there's one more layer of assorted filter components, and this is then we hit bottom. We don't go any deeper than these 3 levels if you count the top level for the splash panel. And here's some other rarely used things to do with filters with non-zero initial conditions and so forth. Now all of these in this sort of cluster right here, which is a major chunk of Speedster, are one sort of filter or another. Here we have resonators and so on and so forth. Now some of these devices, if we drag them out and run those blocks, we always run by clicking on this here. If we want to change some parameter, quite a number of our blocks are controllable and allow you to adjust them and just sort of get a hardware feel for what's going on. These happen to be gains of these filters which we're shoving around. There's a big emphasis in Speedster on instrumentation. So we have down here a set of meters of various sorts, and one more level down, of course. So for example, if you want to measure the energy of a signal, you would grab that. You might grab a display block which allows you to output. You would wire it up. The only thing we need now is a signal generator, so let me get some sort of random noise source perhaps in here, get myself a noise generator and just have a look at how much energy is coming out in a 300 sample blast of that. You can see it's changing like crazy, and of course random, but it's saying it's coming out about 250 units worth of energy. Well, lots of these instruments are here for measurements, and the other thing we have is adaptive and time varying filters. Extremely good environment when you're in Simulink to try to look at adaptive filters, and we have not only our ones, but also, when I say our ones, I mean DSP Speedster, but we've also brought to the top some which come from signal processing block set. But it's not only instrumentation that we can do, we also can do modulation. We have a variety of phase modulators. Here you see BPSK, QPSK, and so on, corresponding, and also and then frequency shift of various sorts, MSK, GMSK, and those sorts of things, as well as emulations of more traditional analog like DSP, double sideband modulators, single sideband modulators, and that sort of thing. So we can harvest these from various places, and again some multi-rate sort of things here which are available from within Simulink, and correspondingly of course demodulators and PSK and so forth if we go down deeper. So there's quite a range of several hundred blocks, some of which are specialist, like this toolkit right here, which is simply to do with DTMF, touch-tone telephony, and the experiments you can do with that. Now when someone first uses this tool, they should, of course, as I mentioned earlier, if they're going to build a model, they should go to the express lane here so that they can get just only the important, most frequently used blocks until you find out where things are and what to do. Let me just take a simple case here of sine wave plus noise typical construct that engineers need, I might get a dual trace scope, bring this in, hook this up. I'm not still too happy yet. I should probably make this a slightly more complicated situation, so I'll break that line right there and I'll go and get myself a filter. This easy filter is a good one because we don't have to be concerned too much about details of how it's being designed internally or whatnot, and I can just leave things dangling there. I don't have to connect anything to that if I don't want to. I've now written a program in very fast time. I run this and have a look. I see on the dual trace scope, I see yellow and white. The white one is coming through here. That's the signal plus noise. You notice that noise is centered out here. We don't quite know where. It's something in the 2 kilohertz region. We can harden this up. With these scopes are extremely flexible. We can, for example, average in the frequency domain by pushing this button, and we begin to start seeing something which is very much like the power spectral density. If we were to in fact do the square of this, start again, and then divide by n, this would actually be the noise spectrum hardening up. If I want to suppress all of that and just look at the sine wave, then of course I see what's coming in on this yellow trace, nice clean sine wave. Another thing that we can do is do synchronous averaging in the time domain, bring the white trace back, start this, and you see that sure enough the sine wave is being enhanced up out of that noise. There seems to be some sort of phase shift. Well, why is that? Well, it's because we're going through this filter right here, and that is causing and imparting a phase shift. If we go back to the spectral scene and start the averaging, and then maybe bring this filter down, all we have to do is click on these things. We can just grab this edge right here and now restart the averaging, and you notice that this is now, in fact, let me get this off so the scale comes up again. You can see that I've begun to bite into this quite dramatically, and start the averaging again. You can see I've just almost removed the noise, and that's shown also, of course, in the upper trace. So there's a lot we can do with our analyzers without having additional hardware blocks brought in. The very first place, however, that you should start in using this tool is the demos section. Here the demos are shown as isolated colored blocks. Here the demos are given in terms of some categories, and if you notice, the categories over here are adaptive processing, of which we have quite a number of demos, comms, a large number of comms, digital filtering, and so on. So they are grouped by their functionality. I usually prefer to run it from here, and you can see them all laid out. There's, I think, 6 of these at current time. Now, some of these are very revealing. They're some of them very simple. Take, for example, a simple sine wave coming through, and let's listen to it. We hear that. We can, of course, change the frequency of this because we have variable oscillators, and we can hear that. So we have simple models, which all the way up to quite complicated ones. Let's take a sort of intermediate one to show some of the things we can do with the scope. Here's a sine wave hitting a half-wave rectifier on this trace, but not on the top trace. So let's run this, and you see that if I kill one or the other, I can see them in isolation. So the yellow sine wave, if I get rid of now the yellow sine wave and look here at the harmonics which are being generated, here's my original 2 kilohertz, here's a harmonic, here's a harmonic. Sometimes I like to do various things, like, for example, I'd like to have a grid on this, and I might like to look at it in dB. When I do this, I can see that, in fact, here's the fundamental, here's the next harmonic, and there's one missing here. I can move this by clicking on this. Most things are done with left button clicks. I move this along and I see my fundamental. I've also, by the way, right clicked and got up a measurement. I can do that and measure things all over the place if I want to, or I can get rid of these little measurement blocks. And I can see that now these things are harmonically related because those red lines are falling there, and there's of course a missing one, and that's due to the nature of the nonlinearity being used. There is for each of these demos a small story which says what it is that you're trying to look at, and usually a reference from the literature where you can go and read independently about this. So we start with quite simple ones. We move to things like, for example, FSK, frequency shift keying. You begin to see models which are quite a bit more exotic. And when we fire up one of these and have a look at some of the spectral things, you can see the noisy FSK signal here is these sine waves are going back and forth. We can average those spectrally, and we start seeing that there's some little ears picking up on here. This is so-called Sundi FSK, and these ears can be used for synchronization purposes. And again, the story now here is for that, and references to a couple of communications books. So there is some description of what you're seeing here, but the value of these little snippets of information is that, to a certain extent, they make for a miniature DSP and comms and instrumentation course, but more importantly, they show the typical way that we build models and some of the tricks that you can begin to use inside your own blocks and your own systems as you begin to build up your holdings and your experience with this tool. When you do have your own keepsakes, you can store them here and have them integral into this Speedster tool if you should so wish. So what you have here with Speedster is something which takes you beyond filters, although filters figure very heavily in this, to systems, and is a perfect platform for algorithmic development.